Welcome, everyone, to The Explainer. Today, we're taking a seriously exciting journey. We're going to move from the very basic foundations of how numbers are classified all the way to discovering some literal math cheat codes. If you've ever wanted to look at a massive, complex calculation and just instantly know the answer without breaking a sweat, well, you're in the right place. Our goal today is to uncover every trick of the notes, unlocking the hidden patterns that make math so much easier.
Okay, let's dive right into this. Here's our game plan. First, the number family tree. Then, mastering decimals and roots. Third, primes and breakdowns. Fourth, the terminating decimal trick. Fifth, advanced divisibility hacks. And finally, number 6, the digital sum secret. All right, starting off with section 1, the number family tree. So, to hack math, we first need to see the map of the territory. Basically, all numbers fundamentally split into two main branches: real numbers and imaginary numbers. Real numbers are the ones you can physically plot on a number line, from negative infinity right through 0 to positive infinity. Imaginary numbers, well, they're the ones that don't quite fit on that line. Take the square root of negative 36, for example. Since you can't multiply a real number by itself to get a negative, we have to pull out the square root of negative 1, which we call I. That leaves us with the imaginary number 6i. But what happens when you mash these two worlds together? You get the third category right at the top of our tree: complex numbers. A complex number is really just the combination of a real number and an imaginary number. For instance, 5 plus 2i. You've got your tangible real part, the 5, and your imaginary part, the 2i. And that perfectly solidifies the top of our number family tree. Let's move to section 2 and see how this builds: mastering decimals and roots. When we zoom in on those real numbers, it brilliantly illustrates how abstract fractions and roots actually occupy a very specific physical space on a geometric number line. You can take the space between 0 and 1 and slice it up into exact fifths. Or think about the square root of 5. By drawing a right triangle with a base of 2 and a height of 1, the hypotenuse is exactly the square root of 5. If you swing that distance down to the number line, it lands right around 2.23. So it's not just a random symbol, it's a real physical distance. Now, not all real numbers play nicely. They actually split into rational and irrational numbers. Rational numbers are the well-behaved ones, right? They can be written as a perfect fraction of two integers, p over q. Things like 5 over 7, or even repeating decimals like 0.444. Irrational numbers, on the other hand, totally refuse to be boxed in. Numbers like the square root of 2, the square root of 3, or pi. They simply cannot yield an exact fractional value. Their decimals just go on forever without ever establishing a clean repeating pattern. Getting closer to the real tricks now. Section 3, primes and number breakdowns. When we're dealing with positive integers, we divide them up into prime and composite numbers. A prime number is exclusive. It has exactly two factors, 1 and itself. Think of 2, 3, 5, 7. On the flip side, composite numbers are the sociable ones. They have at least 3 factors, like 4, which is divisible by 1, 2, and 4, or numbers like 6 or 8. Now, here's where it gets wild. There is a hidden pattern here. Every single prime number greater than 3 can actually be written in the form of a multiple of 6 plus or minus 1. Literally, 6 times n plus or minus 1. For example, 5 is 6 minus 1, 7 is 6 plus 1, 11 is 12 minus 1. It is an absolutely incredible structural rule that dictates how the building blocks of math operate right beneath the surface. All right, welcome to the hacks. Section 4, the terminating decimal trick. So let me ask you this. If you're staring at an ugly fraction, how do you know if it's going to result in a clean, neat decimal or a messy, endlessly repeating one without actually doing the long division? Is there a way to just look at it and instantly know? Yes, there absolutely is. Here is the trick. You only need to look at the denominator. If the denominator is made entirely of powers of 2, powers of 5, or a combination of both 2 and 5, it will be a clean terminating decimal for sure. Take 31 over 8. The number 8 is just 2 times 2 times 2. Because it's only made of 2s, we instantly know it terminates perfectly. And it does, right at 3.875. But if the denominator has a 3 or a 7 in it, like 19 over 6, yeah, that's going to repeat forever. So to use this cheat code, you just follow these 3 quick steps. 1. Simplify the fraction as much as you can. 2. Look strictly at the denominator. 3.
Break that denominator down and check if its prime factors are only 2s or 5s. If they are, you've got a clean decimal. If a rogue 3 or 7 sneaks in there, it's a non-terminating decimal. Just think about how much time this saves on exams or when you're making estimates in the real world.
Let's keep the momentum going. Section 5, Advanced Divisibility Hacks.
So the crucial point here is that when you're asked if a massive number is divisible by something terrible, like 72, you don't actually divide by 72. No way. You break 72 down into smaller, simpler coprime factors. Coprimes are just two numbers that share no common factors other than 1. For 72, those are 8 and 9. So you just use the easy divisibility rule for 8 and the easy rule for 9. If both work, boom, the number is divisible by 72. The exact same logic goes for 88. You just check for 8 and 11. To see this logic in action, just think about how 36 becomes 4 and 9, or 12 becomes 3 and 4. Even something like 90 breaks down beautifully into 9, 2, and 5. By factoring large numbers into their coprime elements, we prove that large, scary math is really just small, manageable math wearing a trench coat. It's an illusion of complexity, and you can easily see right through it.
Let's talk about a specific rule in action, checking if a giant number is divisible by 8. You definitely don't divide the whole massive string. The standard rule for 8 is to just look at the last 3 digits. But there's an even faster trick. If the hundreds digit is odd, like the 1 in 152, you just add 4 to the last 2 digits. 52 plus 4 is 56. Since 56 is perfectly divisible by 8, the entire number is divisible by 8. We found our answer in seconds, completely bypassing long division.
And finally, the ultimate math cheat code. Section 6, the digital sum secret.
Imagine you've just finished a massive, multi-step calculation. How can you instantly verify that your answer is correct without actually doing all that grueling math a second time? Is there a magic spell to instantly check your work? Well, that magic spell is the digital sum. A digital sum is found by simply adding up all the digits of a number until you get a single digit. But here is the massive hack. You can just ignore or cross out any 9s or any combination of digits that add up to 9. Take a huge number like 430,168. Instead of carefully adding 4 plus 3 plus 0 plus 1 plus 6 plus 8, we just cross out the 6 and 3 because they make 9. We cross out the 8 and 1 because they make 9. And what's left? Just 4. The digital sum is 4. It literally takes 1 second. Now here is the golden rule that changes everything. Listen to this. In any valid calculation, the digital sum of the left-hand side will always equal the digital sum of the answer on the right-hand side. Let's look at 22 times 17 equals 374. The digital sum of 22 is 4. The digital sum of 17 is 8. 4 times 8 is 32, and the digital sum of 32 is 5. Now let's check the answer, 374. 3 plus 7 plus 4 is 14, and 1 plus 4 is 5. The left side is 5, the right side is 5. It works every single time to verify your answers.
Let's see how this hack utterly destroys a multiple choice question. What is 842 squared? Normally, that's a ton of multiplication. But using the hack, the digital sum of 842 is 8 plus 4 plus 2, which is 14, which becomes 5. What's 5 squared? 25. And the digital sum of 25 is 7. That means the correct answer must have a digital sum of exactly 7. If you check your multiple choice options, crossing out 9s as you go, only one option will result in a digital sum of 7. You just solved 842 squared in about 5 seconds. 0 actual heavy multiplication required.
And that brings us to the end of our journey today. From mapping out the number family tree to completely bypassing complex calculations with the digital sum, you now have a serious toolkit. We've explored every trick of the notes. So, with these hidden patterns and cheat codes now unlocked, how will you see the math around you differently today? Hopefully, you'll start looking at everyday numbers not as a chore, but as an exciting puzzle just waiting to be effortlessly hacked. Thanks for hanging out with me on this explainer, and keep exploring those numbers.